Supermassive black holes are the largest mass black holes and are found at the centers of galaxies. Galaxies are large collections of stars, ranging from small galaxies, consisting of hundreds of millions of stars, up to the largest galaxies, which can have upwards of 1 trillion stars. Galaxies fall into several categories, developed by astronomers based on their shapes, like spiral galaxies and elliptical galaxies. There are also galaxies that don't fit into the standard classifications. Our classification system has really become a zoo of galaxy types. Among the unusual creatures in the galactic zoo, active galaxies are those which are thought to host a supermassive black hole at their center. Let's visit the zoo. The galaxy NGC 7742 is an example of a Seyfert galaxy. Seyfert galaxies are spiral galaxies with unusually bright central regions. The properties of the light emitted from the bright cores is not typical of regular starlight. Normally, the light from a galaxy is mainly black body emission from the stars, as we learned about earlier. But the central regions of Seyfert galaxies also have a bright emission spectrum, which indicates extremely hot gas. We will learn what an emission spectrum is in a later module. The first quasar discovered, in 1963, is called 3C273. In the first pictures taken of the quasar, its features could not be resolved, and it looked much like a star. However, the properties of this star seemed very peculiar, so it was called a quasi-stellar object. This name was later shortened to QSO, or quasar. Modern images show that the quasar isn't a star, but the ultra-bright nucleus of a galaxy. In the left picture, the quasar is the very bright point of light in the middle of the box. The spikes that are visible are artifacts of how the light is collected by the telescope. You might be able to see faint light from the galaxy surrounding the bright quasar, and there is a jet of gas poking down into the right. In order to take a photo on the right, the Hubble Space Telescope placed a shield over the bright light, which allowed it to take a picture of the galaxy. In 1929, astronomers observed a star-like object that they called BL Lacertae, or BL Lac for short. This thing also looked like a star through a telescope, but its brightness varied so wildly that it could sometimes be 15 times brighter than it was during the previous month. At the time, it was classified as a variable star, but when better telescopes observed BL Lac, evidence for a galaxy could be seen surrounding the bright point of light. Other similar galaxies have since been discovered, and they've been called BL Lac objects, since they seem very similar to the original. More recently, astronomers have been calling these galaxies blazars. When blazars are imaged, we find them at the center of elliptical galaxies. Galaxies are made up of lots of stars, so we expect the light from a galaxy to look like the light from stars. Stars emit most of their light in the ultraviolet, visible, and infrared parts of the electromagnetic spectrum. One thing that stars do not emit significant amounts of are radio waves. That means that normally we would not detect much radio wave emission from galaxies. However, a small fraction of galaxies emit lots of radio waves. We call these galaxies radio galaxies. Most radio galaxies are also giant elliptical galaxies. Active galaxies that are part of this zoo share many similar properties. Typically, they have a bright central object called an active galactic nucleus, or AGN, which is surrounded by the fainter stars that make up the spiral or elliptical galaxy. Have a look at this diagram, which represents a unified model for all of these active galaxies. The unified model for an active galactic nucleus has a supermassive black hole at its center, surrounded by a disk of gas that orbits the black hole and emits lots of energy. In some cases, there is a jet of gas shooting out from the central object. We will learn more about disks and jets in a later module. The model predicts that when you look directly down the jet, you see a blazar. if you look at the jet from an angle so that you can also see into the accretion disk, then you see a radio-loud quasar. If you're looking at the edge of the disk so that the inner part of the accretion disk is blocked, you will see a radio galaxy. If there's no jet, then there will be very little radio emission and you'll see a Seyfert galaxy, which is also something that could be called a radio-quiet quasar. So the difference in the names you call a supermassive black hole really just depend on your point of view. One thing in common with all the active galaxies is that the supermassive black hole at the center is consuming lots of gas, enough to power their energy output. The active galaxies are feeding their black holes, which allows the black holes to grow. The supermassive black holes may have started out as large stellar mass or intermediate mass black holes many billions of years ago and grew over time. On the other hand, sometimes there's evidence for supermassive black holes which aren't being fed tremendous amounts of gas, like the supermassive black hole at the core of our own galaxy. These black holes are quiet and much harder to detect. So just how massive are these supermassive black holes? Although we can't put a black hole on a scale to figure out how much it weighs, we can still measure its mass. Kepler's laws of orbital motion apply to planets, stars, and black holes. If we can find a star orbiting a black hole at the center of a galaxy, then we can determine its mass. The best example is the black hole known as Sagittarius A star, or Sag A star, located at the center of our galaxy. It is possible for astronomers to observe stars orbiting in the region within a few light years of the center of our galaxy. Astronomers have tracked the orbits of these stars for more than 20 years, which can be seen in this video. In this video, the center of our galaxy is marked with a star symbol, and the colored circles mark the position of the false colored stars. Over the years, the stars' paths trace out ellipses. Watch the star labeled SO2. This star, and the others, moves faster when it is closer to the black hole and slower when it is further out, just as required by Kepler's equal areas law. The stars in this video orbit the invisible point at the center of the galaxy in a manner similar to how the planets orbit our sun. We can use Kepler's third law of motion to compute the mass of the invisible object located at the star symbol. The astronomers who measured the mass had to take into account the three-dimensional nature of the orbits of the stars. The star, SO2, takes 15.9 years to make one full orbit. When a star travels on an elliptical orbit, the distance a that appears in Kepler's law is equal to half of the length of the long axis of the ellipse. In the case of SO2, the value of a is 1,000 astronomical units. Kepler's third law for Sagittarius A star is mass of Sag A star plus mass of SO2 equals a cubed divided by p squared equals 1,000 cubed divided by 15.9 squared equals 4 million solar masses. The mass of SO2 is tiny compared to the mass of Sagittarius A star, so we can approximate this as mass of Sag A star equals 4 million solar masses. If you compare the distance between Sag A star and the orbiting star to our own solar system, 1,000 astronomical units would be well beyond the orbit of the planets, extending into the region where comets orbit the Sun. The closest star to us, Proxima Centauri, is 200,000 astronomical units distant. So this is a gigantic mass packed into a tiny volume of space. Whatever is located at the center of our galaxy can't be stars, since we would be able to see them if they were there. A black hole is the only plausible way to get such a large mass into a tiny volume. Our galaxy's supermassive black hole is actually considered a small fry in the heavyweight division, compared to other galaxies' central massive black holes. The giant elliptical galaxy M87 has a black hole at its center that is approximately 7 billion solar masses. You may have heard that galaxies have dark matter, and may be wondering whether the supermassive black holes could be the mysterious dark matter. There are many reasons why supermassive black holes are not galactic dark matter. The most important thing to know is that the mass of a supermassive black hole is just a tiny fraction of the mass of the galaxy that it lives inside. In addition, supermassive black holes are found at the center of a galaxy. The dark matter in galaxies has a mass that is larger than the mass of all the stars in the galaxy and is spread out throughout the whole galaxy in a giant sphere that surrounds the galaxy.